Okay, hi BC Part 1, how are you? So this is the promised screencast, no quotes. Cameron and Daniel are making fun of me for saying watch the screencast and then never posting a screencast, which I evidently did 3 times. So to make up for that, this screencast is going to be 4.5 hours long. Okay, now here's what I want to do. In addition to never wanting to step foot in a swimming pool again after our class today, I want to make sure that we are pretty facile and comfortable with looking at expressions in logarithmic form and evaluating them. So with that in mind, will you please go to your Algebra 2 book and just right now as a warm-up, do number 13 through 18 all. In fact, before you dive in, I'm going to do number 13 right now with you, okay? And these log expressions are a little bit more involved. They look like this, okay? Log base 7 of the cube root of 49 equals what? Now, a couple of things. You know, some of you may be able to very readily see that this is equal to 2/3 right away, all right? But let's say you didn't see that Let's say you didn't see that immediately. And when you have log base 7 of the cube root of 49, maybe you rewrote this as log base 7 of the cube root of 49 equals x, and you're trying to find out what x is, okay? You can always take an equation now. This is an equation, no longer just an expression, right? You can always take an equation written in logarithmic form and rewrite it in exponential form as 7 to the x equals the cube root of 49, all right? And often when we have an expression like this and we're trying to figure out what value of x here will make these two expressions equivalent, it helps to rewrite this right-hand side as a base of 7. So 7 to the x, the left-hand side. I know the cube root of 49 is 49 to the 1/3, right? And I also know that 49 is 7 squared. Okay, so what I've done here is I've just rewritten 49 as 7 squared. And now here I have a power to a power, right? And we have to be a little bit reminding ourselves of properties of exponents. So at the end of the day, this becomes 7 to the x equals 7 to the 2/3. So x equals 2/3. All right. But right now, what I'd like you to do is just go ahead and work through 14 through 18 all. The 15 and 17, the answers are in the back of your book. And when you work them all out, I'm going to go ahead and just do the answers for 14, 16, and 18. Okay, so you have them. So go ahead and do those and then replay me for the answers. Okay, here are your answers to 14, 16, and 18. What I'm going to do is I'll work out number 18 just in case it wasn't obvious to some of you or you got it wrong, you can't see why, okay? So number 18 says log base 10 of 1 over the square root of 1,000, all right? And let's say that it was not immediately obvious to me what this is. I have to do a little bit of work. And if you are in that boat, boys and girls, where you are someone who has to write it out, there's no shame in that. Go ahead and just write it out. I can assure you that it will become easier and quicker with just practice, that's all, okay? All I'm doing now is rewriting the logarithmic equation exponentially. So I have 10 to the x equals 1 over the root of 1,000. And I'm going to try and rewrite this right-hand side as an expression with a base of 10. And I know that 1,000 is just 10 cubed, right? And I also know that the square root of something is the same thing as that something raised to the 1/2, all right? And I know that a power to a power involves multiplying. And now if I look at this, 10 to the x equals 1 over 10 to the 3/2. Well, 1 over 10 to the 3/2 is the same thing as 10 to the negative 3/2. And then now I'm able to say and see what x equals. All right? Okay, so that should have just been a warm-up, okay? And now that leads us very nicely, actually, now on that same page. If you look at questions 19 through 24, okay, so we're still on page 471, look at questions 19 through 24, all of them. What they're asking me to do now is solve for x, okay? Solve for x. Actually, you know what? I'm going to go 19 through, not 24, 19 through 30, all of them, okay? You are solving equations. Those equations, boys and girls, are equations in logarithmic form. And if you scan them with me for a second, look at equations 19 through 24 and note where x is. Okay, note the location of the variable that you're solving for. And then look at 25 through 30 and note where the x is there, right? So in these equations, you're solving for x, but x can be the base. X could be the argument of the log, and just to be clear, if I have something like this, log base 6 of x equals, I don't know, 2, all right? The argument of the log is that which you're taking the log of, so log base 6 of this quantity, all right? The base of the log is this, the number right here, the subscript. Log base 6 of x equals 2. And this is, as you know, what the log expression equals, which you also know is the exponent of the base, okay? So what I'd like you to do right now is go ahead and solve for x in question number 24, and then also solve for x in question number 28, all right? And then replay me for the check solution. All right, for number 24, the equation is log base 1/9 of x equals negative 1/2. All right, and again, what I'm going to do here, since this is my kind of first foray into this world, is I'm going to rewrite this equation exponentially. This is equivalent to 1/9 to the negative 1/2 equals x. Okay, and 1/9 to the negative 1/2, right? Remember our properties of exponents, is the same thing as 9 to the 1/2 equals x. Everyone okay with that? Right? All right. And 9 to the 1/2 equals 3. 3 equals x. Okay, number 28 says the following. 28 says log base x of 7 equals 1. So we're solving. And again, I'm going to rewrite this exponentially. X to the first equals 7. So what must x equal, everyone? Yes, x equals 7. Okay, these are just log equations, logarithmic equations. Okay, now what I'd like you to do is the following investigation with me, all right? Part of your homework here, let's go down to the very bottom and just keep a running tally of what your homework is. Part of your homework here is to work through page 471, numbers 19 through 32, all of them, okay? Obviously, we've already done a few of those above, and we'll come back and add to this, okay? All right, I would like you to take a look at this expression. There is, believe it or not, there is a number that is equally famous to the irrational number pi. Would you like to know what that number is? Yes, there is a number e. What is e, you say? E is approximately equal to 2.718 ... okay? E is an irrational number, equally famous to its friend pi. And here's a question for you, which is, where did E come from? Who stumbled upon it? And in all honesty, boys and girls, the answer to where E comes from and how it emerges is in and of itself a fascinating story. For me to also show you mathematically where E comes from, beyond what I'm going to show you right now, does require some calculus. And so I'm going to ask you be patient with that. But let me tell you what you can explore right now. I would like you to look at this. Look at this expression. Here's the expression. Let's call it 1 plus 1 over x all to the power of x. And let's just let's call that function f of x, okay? So let's call it f of x. So what I'm saying here is f of x equals 1 plus 1 over x all to the x. Now the first thing I want you to do is to sit back and just take a look at this and kind of let yourself kind of toss around this new member to the family. It's a little bit odd. You don't quite know what to do with it. It may say something or do something that makes you feel uncomfortable. Kind of reminds me of, like, you know, that cousin that you don't really see often, and then all of a sudden he appears on Valentine's Day wearing an odd costume, and you say, it's not Halloween, it's Valentine's Day, and they surprise you by saying something a little bit odd. This is odd. Part of you wants to say, oh, it's an exponential function because I see x in an exponent. Part of you wants to say, well, there's kind of a rational function thing going on here, right? But believe it or not, this function is neither one of those. In fact, this function here, believe it or not, defies classification. There really isn't a category under which this function falls. And this expression has defied and mystified mathematicians for, can I say centuries? I think I can say centuries, and continues to be a source of mystery for this reason. As x approaches positive infinity, what do you think f of x approaches? And let me share with you the story of kind of how people have made this conjecture about what f of x approaches, okay? So one camp says the following. This is camp 1. Camp 1 says, as x gets big, 1 divided by x approaches 0. And if 1 divided by x approaches 0, that means 1 plus something approaching 0 approaches 1. And if this is approaching 1, 1 raised to no matter what power it is, this whole thing has to approach 1. So one camp argues the following. They will say, okay, let's call this camp 1. They will say f of x approaches 1. And yet there's another camp. And the other camp does this. They say the following. They say x is approaching infinity. Wow, x is approaching infinity. The exponent is approaching infinity. And if the base is bigger than 1, which they argue it is, because 1 plus something will always be bigger than 1, anything bigger than 1 raised to the infinity, they would argue f of x must approach positive infinity. Now, I think you'll agree with me that in this war of ideas, and it is a war of ideas, and in the history of math, there are many examples of mathematical ideas being heretical. To utter certain things would be heretical. And believe it or not, this was once a bone of contention, that on one side we had a function that approached 1 as x got very, very large. On the other side, someone saying as x approaches positive infinity, f of x approaches positive infinity, right? Two warring factions. And I have to go back and look at the history books and tell you exactly how long this war of ideas went on. But at some point it was resolved inarguably that, in fact, I think this deserves a thick marker. In fact, what we find is the following. In fact, what we have is the following. As x approaches positive infinity, and maybe you're playing on your calculator with this, and you're seeing this on your own numerically, as f of x approaches positive infinity, f of x doesn't approach 1. it doesn't approach positive infinity. It approaches this crazy, unpredictable, irrational number, 2.718 dot, 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 dot. Okay, this number is irrational. And some would argue, some make this argument, see, f of x approaches 2.718 dot, dot, dot. This number is closer to 1, so this team won the argument. And I'd make the argument that not really. I mean, I guess, yes, numerically 2.718 is closer to 1. But when you're talking about behavior as x approaches infinity, I could also make the argument that, I don't know, you were pretty far off here, team 1, okay? So this surprising result, this irrational number that this mysterious function approaches, was given its own name. And this name, the name of that number is, or the name of this crazy irrational number is in fact E. Okay, E is this irrational number that emerges in the context of the end behavior of this function that has no classification. And it's quite bizarre, isn't it? Okay? All right, so why do I say all that? Oh, let's not lose our homework right here. Let's just keep that. I don't want to keep making space. I keep forgetting to come back. Okay, so why do I tell you this? Well, first of all, two things to keep you in a state of suspense, because we will go back and revisit this particular function and see the connection between it and this new member of our crazy family, E, right? But also, I want to share with you this idea. E has kind of earned its respect, earned the respect of the mathematical community, in that it turns out that E is awfully convenient. One place it becomes very convenient is in certain growth applications. But before I go into those in particular, I do want to talk about logs of base E. Yes, indeed. How on earth could we have a log of base E? Let's start this way. What is log base E of 1 equal to? In fact, while we're here, what is log base pi of root pi equal to? While we're thinking of weird, this is saying pi raised to what power will equal root pi? And maybe you're someone who will rewrite this out exponentially, or maybe you see it, but here this answer is 1/2. Okay, what is log base E of 1? E raised to what power will yield 1? That answer is 0. Okay, but I bring up the possibility of log base E because log of base E can be rewritten as the natural log of 1. Okay, or the natural log of whatever this number is. So natural logs are logs of base E, just like common logs are logs of base 10. And when you have a natural log, you don't need to write the subscript E. You can just use this notation, ln, natural log. And I find myself sometimes going cursive. Like I'll do this, right? Natural log of E squared. Again, unwritten but understood, there is a base E here. All right? So you now have the ability to, ooh, that's a really funny one. Okay, why don't you evaluate these 3 natural log expressions and then replay me with the answers? Well, the natural log of 1 over E is just going to equal -1 because E raised to the -1 equals 1 over E. The natural log of 0 is asking you E raised to what power will ever equal 0? That's correct, none. This answer, or this log expression, does not exist. The natural log of E of 5th root of, the natural log of the 5th root of E, I said that correctly. This means log base E of the 5th root of E. This equals 1/5. Okay? All right, so in addition to your homework up here, which you already have, I would also like you to do this homework. There it is. There it is. All right, that is your homework for the weekend, and I will see you on Monday for our short period, and you'll have your take home due then as well. Okay, good day.